It's not trivial. It's not trivial. Can be done, okay? But it's not trivial. Let's see, as the procedure that we've seen before returns both the constitutive equation and the dissipation. So, constitutive equation. The stresses are the derivative of the free energy with respect to the strains. The free energy is that. I differentiate that with respect to the strains, and this is the stresses are, this is a mistake, so this is that derivative of C times epsilon minus beta, okay? So, sorry, that one. By differentiation with respect to epsilon is just the case that we had here, but now, I mean, we just then differentiating that with respect to beta. So this is the differential of that with respect to this variable, okay? By the way, I can just take the right version of that. Sigma dot equals C is constant, because that's an elastic material. Material properties are constant a long time, times epsilon dot minus beta dot. And by the way, in virtue of that, beta dot, which is that is 1 over eta times sigma. I replace that. So I obtain this equation that says I can just solve, multiply by C minus 1 here and pass the other term to the other side, says that the strains, epsilon dot, equals C minus 1 sigma dot plus 1 over eta times sigma. Is that a constitutive equation? It is. Because if I know the stresses at a certain point, I know the history of the stress, or the rate of change of the stresses, then I can know the rate of change of the strains. So this is an ordinary differential equation that can be integrated, but at any time after integrating, this is the sort of constitutive equation, but it's not an algebraic equation. It's an ordinary differential equation, but it is a constitutive equation in the sense that if I know the stress and as a function of the time, I can compute the stresses, the time derivatives, and compute the rate of the strains, and integrating the strains, I could compute the rate of the strains, I could compute the strains. That's not trivial. What is that? Okay, now I need some additional integrator. That's not a problem, but that's the constitutive equation. What about dissipation? Dissipation now is minus, according to the theory, the derivative of the free energy with respect to the internal variable times beta dot. Differentiating that with respect to beta is the same that differentiated with respect to epsilon by changing the sign. So it's minus C epsilon minus beta, that's this differential, times beta dot. So finally minus plus is that value here. Just some manipulation, epsilon minus beta, by the way, is the elastic. Epsilon looking at epsilon minus that, which is beta, is the elastic strain. So that's the manipulation here, the elastic strain, and this, the elastic strain, is, and then also sigma is equal eta beta dot, something that I have from the evolution equation. So the dissipation, looking to that, is all this, which is sigma, all this is sigma, times beta dot. But sigma is at eta times beta dot. Finally, one possible expression of the dissipation is eta times beta dot times beta dot. What is the conclusion of that equation? Again, this is greater than 0, and then again, the dissipation equation imposes that the viscosity has to be greater than 0. Okay? Well, I've played with this composite model I recall, in a strain-driven model. What about a stress-driven model? What about if I wanted to formulate the equation of that, or the equation of this equivalent material in a stress-like variable? Okay, a stress-like context. Then, what will I do? I will consider the free variable, the stresses. The internal variable, the same. And then dependent variables are the strain and the Gibbs potential. And the evolution equation is the same than before. Okay, beta dot will equal 1 over eta times sigma. Okay? So, the potential, the Gibbs potential would be the Gibbs potential of the model 1 plus the Gibbs potential of model 2. The Gibbs potential of model 1, we know that since an elastic material, it has to be 1/2 of the quadratic form times 1/2 of the stresses in terms of the inverse of the elastic properties, and the Gibbs potential of a dashpot. We saw in the previous model that the Gibbs potential of a dashpot is sigma times beta. Sigma being the stress, beta being the strain of the dashpot. Okay, so just I consider that, and the total Gibbs potential will be the sum. So this plus this. That's it. I've done. I'm done. So now everything comes out automatically. What is the constitutive equation? The constitutive equation says that the strains would be the differential of that with respect to the stresses, which is then differential of that with respect to the stresses is c minus 1 sigma, plus the differential of that with respect to the stresses is beta. Okay? So epsilon dot is c minus 1 sigma plus beta dot, by just taking rates, c minus 1 sigma dot plus beta dot is 1 over eta times sigma, according to the evolution equation. And by arranging this term, I found this constitutive equation. Look at the one that we saw before. That. No, what is it? No, sorry. That is the one that we found in the strain-driven model. Okay? What is the one that we found in the stress-driven model? It's the same. Of course. It should be the same. But I could have started or look at the model as a stress-driven or strain-driven. Finally, the relationship is going to be the same because I'm representing the same mechanical behavior. What about the dissipation? Again, the dissipation, now written in terms of that, the Gibbs function is the derivative of the Gibbs potential with respect to beta times beta dot. The derivative of Gibbs potential with respect to beta is sigma times beta dot, which is 1 over eta times sigma. So finally, it's 1 over eta times sigma. That is positive. So again, the conclusion of the dissipation equation is that the viscosity is greater than 0. Okay? I'm intending you to get familiar with the way of playing with those concepts. Okay? It's just a game, so to speak. Let's do something a little more complicated in viscosity models, what is called the Kelvin's model. Kelvin's model is a combination in parallel of an elastic model and a dashpot. Okay? So, look that we apply a stress, and this stress arrives, it's split into two parts. So we can consider that the stress is the sum of the stress that goes through the dashpot plus the stress that goes through the elastic model. So I can say that sigma equals sigma 1 plus sigma 2. Okay? By the way, sigma 1 is the stresses in the elastic model, so I call this stress elastic because it's going to be related to the strain in elastic manner. And sigma 2 is minus, I define sigma 2 as minus the inelastic strain. So that recalls the inelastic model based on strain decomposition we have seen before. The total stresses are the sum of one elastic stress minus an inelastic stress. Okay? Okay, now we see that both strains, both models share the same strain. Okay, contrary at what we saw before, in which in the maximal model, which are in serial, they share the same stress and they sum the strains. Here, they share the same strain and sum the stresses. Okay? So, now, that suggests me the following model. For instance, in a stress-driven model, I consider the stresses as the free variable. The internal variable is the strain of the dashpot. Okay? Which I don't say that is equal to the total strain. I just consider the strain of the dashpot as the internal variable. Okay? Then the evaluation, since looking just at the dashpot, the evolution equation says that the rate of the strain of the dashpot is 1 over eta in times the stress sigma 2 on the dashpot, which by the way is the total stress minus the elastic strain. And by the way, the elastic strain is C times beta, which is the strain times the dashpot, the strain on the dashpot. So now let's consider the Gibbs potential. What is the Gibbs potential of an elastic model? 1/2 the stresses C minus 1 sigma 1, which is, by the way, sigma 1 is equal times C times beta. Some operations, this gives 1/2 beta C beta, okay? Which is a specific case of the potential, the Gibbs potential being just function of the internal variables and not of the stresses, but it's just not breaking the rule. What is the Gibbs potential of the dashpot? We know is the stress times the beta. We have seen that a couple of times. So that is the stress, that the sigma 2 is sigma minus sigma 1, and sigma 1 is, so this is sigma beta minus sigma 1 beta, but sigma 1 is beta in C, so finally is that expression here. What is the total Gibbs potential? The sum of both. So this is 1/2 of BCB minus BCB, this gives minus 1/2 of BCB, beta CB, plus, what is it? Plus, now I'm lost. Plus this one, okay? Plus sigma beta, okay? So finally, in a natural manner, I can just formulate this as the Gibbs potential. Okay, that's it. Once I have the Gibbs potential, everything is done. What is the constitutive equation? That one that says that the strains will be the derivative of D with respect to the stresses. So let's do it. The strain as the derivative of Gibbs potential with respect to the stresses, and that is that due to this equivalence, the derivative of G with respect to the stresses, look, the derivative of G with respect to the stresses is just beta. Okay? So that epsilon is equal to beta. It's again the same case. That says that the strains are equal to the internal variable. Okay? The constitutive equation said that the strains are exactly point-wise equal to the internal variable beta I've taken. And then, of course, I can just, the dissipation, take the dissipation would be the derivative of G with respect to beta times beta dot. The derivative of G with respect to beta is sigma minus the derivative of D with respect to beta, which is C times beta. So sigma minus sigma beta is sigma 1, which is beta dot. Finally, we obtain that expression by dissipation. And again, we see that the consequence of that is that viscosity has to be greater than 0. What about a strain-driven model of this? Well, again, I would have to consider the strain as the free variable, okay? The internal variable would be beta, which at the end of the day is going to be the same strain. So it cannot happen that epsilon being the same rate, free variable whose rate can take any value, and beta being an internal variable whose rate is limited by the evolution equation. That's a contradiction, don't forget it. This model cannot be formulated in terms of a strain-driven problem. But fortunately, it can be formulated as a stress-driven problem. That's why we have two options. Sometimes both are possible. Sometimes we have to resort to one of them to formulate the model. If one is not possible or leads to any contradiction, we just go to the other. And that's it. That's the end of the toughest part of the course, I guess to say, okay? So this is theoretical, but you needed to know it, okay? Because otherwise we wouldn't understand something that what is coming, okay?